final. Maybe not. So if you have questions, you can directly mail me or TAs, or you can also use the Q&A board in the Blackboard. Okay. So far we learned the method developed for object detection. So you may remember before the midterm we learned the two-stage method for detecting objects. Okay. So the RCNN, that is the method that apply the CNN for some windows, okay? So obtained from the object, selective search algorithm, okay? That selective search algorithm makes 1,000 to 2,000 bounding boxes that may contain object. And we apply the CNN for those bounding boxes and classify those features, okay? That is the regional CNN algorithm. And to accelerate the RCNN, their speed, and also to improve their accuracy, this fast RCNN has been proposed. And here you will apply just CNN one time on the entire image. Okay? And you can get this type of 2D feature map. Okay? Because the spatial information of the original image will be retained in this 2D feature map. So you can attach the feature map, in the level of feature map, instead of attaching the images in the image level, you can do this. Roughly, they are same. Okay, so you can, but the merit of this method is you can just apply CNN one time. Okay, but in RCNN method, you have to apply CNN 2,000 times if there are 2,000 bounding boxes. So the accuracy, the speed is a lot improved. And after attaching the feature, and you can apply ROI pooling method to convert these arbitrary sized patches into fixed dimensional feature. And then you apply FC layer to map it to the new bounding box coordinate and also the semantic class probability. Okay? That's the RCNN method. So their merit is you can just apply CNN one time on the entire image. So the speed is greatly improved. And also the accuracy is also improved because you can, when classify each patch, you can also consider some of the contextual information inherent in the image. But in here, in RCNN, you can somehow classify each patch, okay? So you cannot exploit some contextual information around those patches. But here, basically, those features are having some contextual information, so the accuracy could be also improved. Okay, that's the fast RCNN. And here is the faster RCNN. There are some bottlenecks in the selective search algorithm, which is not that optimal. So here you can also involve region proposal network that can also infer the optimal bounding boxes. So by doing so, you can improve the accuracy at the same time, you can improve the speed at the same time, you can improve the accuracy. So this is the comparison with these three methods. Time, RCNN is very slow, almost takes 1 minute to detect object from an image. But fast RCNN, it takes a few seconds. But faster RCNN, it takes within a second to detect the object from an image. And this is the accuracy. And you can see their accuracy is becoming higher, which means becoming better. Okay? And this is another testing data, and you can see those accuracies also improved. Okay? This was the two-stage algorithm for detecting object. They are called as two-stage because at the first stage, they somehow detect bounding boxes which may contain object, and then classify their probability, class probability in the second stage. So in that sense, they are called as the two-stage method. And also we also learned about the transformer-based algorithm. So that is called as the DTR-based method. So that's composed of the encoder and decoder. Okay. So here encoder, we somehow improve the image feature. So this image feature is, to say, extracted from CNN already. So we involve the pre-trained ImageNet pre-trained. We normally involve the ImageNet pre-trained CNNs, such as the ResNet, to extract the image feature and input it to the encoder to apply some self-attention mechanism to improve image feature. So here you can again get the image feature which is improved from the original image feature. So you can think by applying some self-attention mechanism, you can improve their feature. Okay, and in the decoder, you can mix image feature extracted from the image, and actually you can mix those with some object queries, and these object queries actually becomes one prediction. Okay, so and you have to set the number of queries. That's the hyperparameter actually. We normally set it to 300 or maybe 100 to 300 or even larger. Okay, I mean, if it fit to your memory, then you can also increase the number of queries. But normally we use this number. So there are 300 number of object queries, which is the random vector, okay? And their values are decided during the training, okay? Anyways, this random vector, which is updated during the training, is cross-attended with the image feature, and they are eventually mapped to the sum of the bounding box and the class probability. Okay, so each queries are mapped to bounding box and their class, and there are 300 number of predictions in your transformer. Okay, and for some of these 300 number of prediction, there would be the bounding box, which is close to the ground truth. Okay, we can somehow measure their uncertainty as well and filter out the bounding boxes whose score is less. Okay, and we can remain during the inference. We can remain only the prediction whose score is high. Okay, that's the DTR-based method, and thanks to the robustness of the transformer, their attention mechanism, nowadays we are using this attention mechanism. Okay. But thing is, DTR-based, the original DTR-based method, they are very slow. Okay, and also this two-stage method, they are also slow. Okay. So today we will learn about some real-time pipelines for achieving the object detection. Okay. So maybe you have heard about this YOLO algorithm, which is the very popular object detection algorithm. It exhibits the very high speed. Okay? So it reaches the 30 FPS, which is the real-time speed. The FPS means frame per second. Okay, so 1 second, how many frames are processed? That's the concept of the FPS. And if you say 30 FPS, it means you can process 30 frames per second. Okay, so it's very fast. So I mean the number, the value here becomes higher. It means your algorithm is becoming faster. Okay. So YOLO, this is the one-stage algorithm. So in two-stage algorithm, I said the algorithm first detect the bounding box, and later it classify those bounding boxes. Okay, but in one-stage algorithm, they do two things simultaneously. So they detect bounding box. At the same time, they classify the probability, semantic probability. Okay. In one stage algorithm, they do two things simultaneously. So in this given input image, they first divide it into several grids. So in this figure, you can see there are 7 by 7 grids. Okay? You divide the whole image into 7 by 7 grid. Okay, and for each grid, you will estimate 2 bounding boxes. Okay, and also classify that grid. Okay. So as I told you, they are doing these two things simultaneously. So for each grid, they estimate 2 bounding boxes. They are doing the first thing. At the same time, they are classifying the semantic probability. Okay, they estimate the semantic probability for this grid. Okay, so indeed, they are doing these two things jointly. Okay, so they are called as one-stage algorithm. At the same time, because of this, they can achieve the real-time speed. And YOLO, their name comes from this full name. So you only look once. Okay. So indeed, this is actually highlighting their one-stage characteristics. Okay. Instead of seeing images twice, as the two-stage algorithm does, this YOLO is doing the joint estimation of the bounding box and also the probability estimation. Okay, so that's why they are called as one-stage algorithm. And here, as you say, there are many bounding boxes estimated, but they apply the post-processing algorithm called as NMS to filter out some redundant bounding boxes. So this is called as non-maximal suppression. So based on the score, they only retain the bounding boxes whose score is high. Okay, and if some bounding boxes, their scores are not that high, but have many redundancy with the higher bounding boxes with higher score, then they will be filtered out. So that algorithm is called as NMS, and this is actually very simple. Okay, so this is their whole pipeline, the YOLO. Okay, and this is actually the core mechanism of this YOLO algorithm. Okay, so as I told you, they will estimate 2 bounding box candidates for each grid, At the same time, they will classify grid into 20 semantic classes. So for each grid, you will estimate this 30-dimensional vector. Okay. So because you will estimate two bounding boxes, one bounding boxes is composed of 5-dimensional information. So because of that, you have to estimate 10-dimensional vector for estimating information about two bounding boxes. And also you have to estimate 20-dimensional vector to estimate the class probability for those grid. Okay, so I mean, because there are 20 number of classes, to classify each grid into classes, you have to estimate 20-dimensional vector. Okay, so these 30-dimensional vector are estimated from each grid. As a result, you have to estimate 7 by 7 by 30-dimensional array as the output. Because there are, as I told you, there are 7 by 7 grid, okay? And for each grid, we will estimate 30-dimensional vector, which have the information for two bounding boxes and 20 number of classes, okay? So there should be a 7 by 7 by 30-dimensional array as the output. Okay. Are you guys following this? Okay. So given whole image, you have some differentiable component, okay? And your output have to be 7 by 7 by 30-dimensional array, okay? So, I mean, you have to train the middle layers to estimate this dimensional array. I mean, of course, the dimension of the final output could be changed if you use different data set. If the new data set had, for example, 40 classes, then this dimension have to be changed to 40, and your final output, those dimensions have to be changed to 50, okay? So you have to estimate 7 by 7 by 50 dimensional array. And also, if you want to change the grid number, maybe you sometimes want to increase the grid number to maybe 13, okay? Then you have to estimate this dimensional array, okay? And also, even you can also want to estimate more bounding boxes for each grid. Then, for example, if you want to increase the number of bounding boxes estimated for each grid to 3 instead of 2, then this, and also if you have 40 number of classes, then the overall dimension should be changed to 55, okay? Then this should be changed to, for example, like this, okay? So anyways, these numbers can be changed by yourself, okay? You can design it really, okay? But anyways, the entire YOLO algorithm works like this. So given image, you are actually estimating both bounding box information and the semantic class probability for each grid at one time, okay? So this is the YOLO algorithm. And also, I will show you why 5-dimensional information was reserved for each bounding box, okay? So, I mean, I said to you, for each grid, we will estimate 2 bounding boxes. That's the default setting, but of course you can change it, the number of bounding boxes. But for each bounding box, you have to contain this 5-dimensional information. So the first thing is the X and Y coordinate of that bounding box center position. So we have to specify it, okay, their center position. And also we have to specify their width and height. Okay. So this 4 dimension is actually essential for describing one bounding box. Okay. And the last thing we have to have is the confidence value. Okay. So this confidence value is actually is having actually this information. So what PR object means is this becomes 0. This have either 0 or 1. Okay, I mean if for example, if when making the ground truth, okay, if grid location is here and when making the ground truth, this confidence value have to have 0 for this grid. Sorry, not this grid, because there are band here. Actually, if the grid is here, then from this grid, I mean, there would be no object in the image. So when making the ground truth, you have to assign 0 probability for this object needs. Okay, so so this have to be 0 for especially this grid, and also regardless of which number this IOU value have, I mean this confidence value will go to 0. Okay, for background grid, you have to make your ground truth confidence value as 0. Okay, but for grid like this, or this, having foreground object, you have to set this object probability as 1 and multiply with your IOU value with ground truth bounding box and your prediction. Okay. So you will have, you will predict some bounding box, for example, bounding box from this grid, okay? And let's say there are ground truth bounding boxes are like this for this bicycle. But if you, from this grid, you estimate the bounding box like this, okay? Then you can measure how accurate your predicted bounding box with by comparing it to this ground truth bounding box. That measure is actually this IOU. So you have to train your network by producing your IOU value with this one object needs. Okay? If that grid is having object inside, this would be the ground truth value for this confidence. Okay, but if that grid is not having any object inside, then this confidence value is simply have the 0. Okay. So, anyways, I will also re-explain about this IOU and some more details in the later slide. But you can now become aware of why this one bounding box is having 5-dimensional information. Okay? So X and Y coordinate for center positions of the bounding box, and also the width and height. That's the 4-dimension value. And also you have to have this confidence value. And actually using this confidence value, as I told you, this NMS, non-maximal suppression, is performed. So among these many bounding boxes estimated from our network here, okay, we have to choose very good bounding boxes. Okay, there would be many redundancy between these bounding boxes. So based on this confidence value, we will choose the bounding box whose confidence value is large. Okay, that's the non-maximal suppression algorithm. And I will tell you, explain about this IOU measure. Okay, this is the abbreviation for intersection over union. IOU means intersection over union. When measuring how close these two bounding boxes are, we normally use this IOU. So IOU, as I told you, their name is coming from this intersection over union. Okay, and when calculating this IOU, in the bottom you will calculate the area for union region of these two bounding boxes. Okay, so if two bounding boxes are located like this, you have to calculate their union area and put it in the bottom. Okay, and this top part, you will calculate the area of overlap regions between these two bounding boxes. That would be here. Okay, this is also called as the intersected region. Okay, so how many how many intersections are say the portion of the intersection among this union region. That's the IOU measure. So if two bounding boxes are exactly same, then this IOU will become 1 because their intersection is actually same as the union. Okay, so actually intersection over union, but union is actually same as intersection in this case. So the IOU becomes 1. And if two bounding boxes does not have any intersected region, then this IOU will be 0. Okay, simply this part becomes 0, so the entire IOU will become 0. So this IOU is the measure to calculate the similarity of two bounding boxes. If they are exactly same, the IOU, the similarity between two bounding boxes, close to 1. And if these two bounding boxes are completely different, their IOU values become 0. Okay, so IOU is the measure for calculating the similarity between the bounding boxes. Okay, so here we are actually calculating the IOU between the ground truth bounding box and the predicted bounding box. Okay, so it will become close to 1 if our prediction is same as ground truth. Okay, but it will become close to 0 if they are different. Okay, so it means if they have object inside and the outputted bounding boxes are close to ground truth, then their confidence value will be close to 1 unless they will close to 0. Okay, so after training, given estimated bounding box, we can filter out the bounding boxes based on these confidence values. Okay. Okay. So in YOLO, original YOLO, from each grid, we will estimate the two bounding boxes and the class probability for each grid. So there will be, in the original YOLO, using the original data set, because there are 7 by 7 grid, and in each grid, we will estimate 2 bounding boxes. There will be 98 bounding boxes estimated from 1 image. And for each bounding box, we have the class probability. Okay, that's the original YOLO. And this YOLO was published in CVPR 16. Okay, almost 10 years ago, this YOLO was proposed. And this is the actually loss function to train these intermediate layers. Okay, so this coincides with what we have learned. Okay, so the first term is actually closing the XY coordinate, center coordinate of the bounding box with their corresponding ground truths using the Euclidean distance. Okay, and actually this flag is meaning, I mean, if those grid is having object or not. Okay, so for example, for this grid, this kind of grid, because they are containing the foreground object like van, bicycle, or dog. Okay, so their objectness flag is 1. Okay, but for this kind of grid which do not contain foreground object, this flag becomes 0, and instead no object flag have 1 value. Okay, so there are actually 2 types of flags here. So object flag and also the no object flag. Okay, so the loss function is applied for bounding box predictions from foreground, from the grid which have the foreground object inside. Okay. So for grid, actually this is the summation for whole grid. S is the grid index. So S is 7 because there are 7 by 7 grid. So because there are grid for height and width, there are 49 grids. So this is the iteration for grid. And this is iteration for 2 bounding box estimation. Okay, so there would be 2 bounding boxes estimated for each grid. Okay, so we have to apply this type of laws that can close our predicted center position of the bounding box to their corresponding ground truths. This number, because there are 98 bounding boxes, as I told you here. Okay, you have to iterate it for all the bounding boxes estimated. Okay, and if they are foreground grid, they apply these laws. Okay, and also you will also apply this type of width and height prediction, and you have to close their width and height prediction to their corresponding ground truths. Okay, and this is also saying you will have the confidence value. Okay, and you have to apply these laws for closing their confidence value to the ground truth 1. You have to make this ground truth by yourself, actually. So for the grid having the foreground object, this confidence will be the multiplication of 1 with IOU. Okay, but if you actually divide this into 2. So for the no object grid, you will simply set this ground truth confidence value as 0, and will make this your predicted confidence to 0. Okay, and you have to also set this hyperparameter, which is actually the constant, to balance this term to other foreground grid terms. Okay, and also this is the term for this class probability. There would be 20-dimensional vector for estimating the class probability, and you will make them close to their ground truth. Here they don't use cross-entropy laws, instead they use Euclidean laws, like this, okay? Okay. So, and also you will not iterate it for this B, because there will be one class probability for each grid. So this is the loss function, okay? Not that hard, okay? And actually, you have to, when implementing this YOLO, you have to, make your ground truth. This ground truth have to be this dimension, okay? But originally, you have bounding box and label vector. So, for example, for the image, you will have maybe, for example, 2 bounding box as ground truth, and having 2 label for these 2 bounding boxes. Okay, that would be this kind of information. This box is having the list of bounding box given to your original image, and you have the label information for this region. Okay. And given these 2 information, you have to make this dimensional array, okay, to train your own network. Here, your final output is 7 by 7 by 30 dimensional array. So you have to, by yourself, make this from your list of the bounding box and list of labels. Okay. And sorry, this is the code for doing that. Actually, I will deliver some concept for this. So what they are doing here is, for each grid, maybe we are using, let's assume that we are using 7 by 7 grid, okay? And for maybe, for maybe this bounding box, okay? You have to make those grid, actually they will have 30-dimensional vector. This grid will have 30-dimensional vector, and this grid will have 30-dimensional vector, so on. Okay. For this grid, you have to calculate their center X, center Y, width and height for 2 bounding box. Okay. CX, CY, W and H for 2 bounding box, and also have to calculate the C multiplied with IO, okay? And also you have to calculate these things, and have to have 20-dimensional, okay, the probability. So you have to assign these values by yourself, and that's actually this target value is having this 7 by 7 by 30 dimensional array. You initialize this as the 0 array, the array having 0 values, and you loop through these ground truth bounding boxes and make corresponding grid their values. You will fill those values with appropriate values, okay? So anyways, you have to have this kind of code to convert your ground truth boxes and label information for this output dimension arrays of your network, okay? So, and also you have to apply non-maximal suppression at the end of the YOLO algorithm, okay? So if you train this network, and after training, when given some image, you will get this 7 by 7 by 30 dimensional array, And if you visualize it in the image, then you can get this amount of predictions. Okay, there will be 98 bounding boxes for each image estimated from your network, and they will have a lot of redundant predictions. Okay, and for example, uh, for this part, I mean, you have to select the bounding box which has the highest confidence, okay, and filter out all other bounding boxes that have less confidence value, at the same time having high IOU value with the highest bounding boxes. Okay, that's the non-maximal suppression algorithm. Okay, so you have to, among these many redundant bounding boxes, have to choose one bounding box having the highest confidence value. Okay, that's called as the non-maximal suppression, and this would be your final output. And NMS, there are many ways to implement that, but this is one example of this non-maximal suppression algorithm. So you have to first sort your scores. This will be the confidence value for your bounding boxes. You first sort it, okay? And you iterate it until, I mean, there will be no bounding boxes remained, which has less, how to say, less unique bounding box remained. So, for example, here you will first sort the bounding box, okay, and how to say, so at the first time, this order 0 will have the highest, will have the bounding box having the highest confidence value. So you will, this keep is the new list of the bounding box. We initialize this here. So from this order list, which have the all bounding boxes inside, and they are also sorted. From those lists, you will make new keep list, which have unique bounding boxes. So because at the first, this order 0 will be the bounding box which have the highest score. So you directly keep it in the keep variable. Okay, and you calculate the IOU between those bounding boxes having the highest confidence and others, and you calculate also the IOU. Okay, so this is the calculation of your interactive region, and this is the calculation for union region. Okay, and if there is no bounding boxes remain having, this is actually calculating the list of bounding boxes having less IOU with the highest bounding box. Okay, if there is no bounding box remained in the list, then this non-maximal suppression is actually done. Okay, so you will actually finish this loop. Okay, so this loop will contain continues until no items are remained in the original list. Okay, and also at the same time, if there is no bounding box remained, which is actually unique from the highest bounding box with having the highest score, so you will finish that, finish the NMS here. Okay? Unless you will get another, the next highest bounding box, and you will continue this process. Okay. Actually, this is not that hard logic, so you can follow this using the code. I mean, and you return only the unique list of the bounding box here. Okay. That's the non-maximal suppression algorithm. So what they actually does is actually from these redundant bounding boxes, having choose one bounding box having the highest confidence value. You can actually, I mean, other than this NMS code, you can implement that by yourself, maybe. Okay. So far, this is the I mean, the algorithmic flow of the YOLO algorithm. As I told you, actually this figure is having all information. From the original image, you will divide it into the grid. And for each grid, you will estimate both bounding boxes and also the semantic class prediction. And by applying the NMS, you will filter out redundant bounding boxes. And this would be the output of the YOLO. This is very simple algorithm, actually. But of course, because of this simplicity, there are some weaknesses in YOLO algorithm as well. So maybe I will continue this next class, but I will highlight this part. So YOLO, it is high localization error, which means sometimes the bounding box, their locations are not that accurate and having the low recall. Okay. So recall, for explaining this recall, I have to explain this part. But anyways, recall is roughly, you can see, the coverage of original ground truths. Okay. How the original ground truths, they can be covered by our prediction. That is the recall. So for example, let's say there are two bounding boxes in the images. If your algorithm is estimating just one bounding box, then your precision would be 100%. If your output is having just one bounding box, which is very close to original ground truth here, and there's no further output, then your system's precision is 100%. Because it predicts this, and this coincides with original ground truth. So this prediction is correct one. So your precision is 100%. But there is something wrong. I mean, this ground truth was not covered by your system, your model. Okay. In that case, the recall becomes lower. I mean, for actually this example, recall is 50% because you have two ground truths, but just one is covered by the model prediction. So there are two, but just one is covered. So this is 50% recall. Okay. So other than the precision, recall is also very important measure for this object detection task. Okay, but this YOLO is suffering from low recall because, as I told you, only 98 bounding boxes are estimated from our YOLO model. So, I mean, if let's assume that there are 200 object inside an image. Okay. Let's assume this case, then I mean maximally 98 objects will be covered by this YOLO, but remaining 102 objects will not be covered by YOLO model, right? So basically, their bounding box, number of bounding boxes are small in scale. Because of this, YOLO version 1, published in 2016, that are suffering from this kind of low recall. So subsequently, there are some effort to increase this low recall problem. Okay, so I will tell you about that in next class. Okay. Anyways, thank you, and see you in this Wednesday again. Okay. Thank you.